pulling strings. Oh God, I'm hungry. I can smell my dinner. Dinner is ready. So this is hard. So another rheogram, Newton's law. Remember, was the shear stress was viscosity times shear velocity. This Newton equation corresponds logically to what we call Newtonian fluids. So this is a linear relationship. I got this in the lab, right? The horizontal one, there's a small variation because the fluids are real, and then viscosity is not exactly constant, because of the noise of the instrument and impurities or whatever. Okay, and if you plot the shear strength versus shear velocity, you got very well aligned, and the slope, this is for type 1, right? The slope is the viscosity. Okay, so the second rheogram is used to predict how viscosity is. So this is to study viscosity behavior, and this rheogram, which is tau shear velocity versus gamma dot shear stress versus shear velocity, is to predict viscosity, because science has to fulfill two objectives: explain what we see and predict new events, okay, or future events. The second type, the shear thinning, has a behavior like this too, and the equation is similar, but no, not similar, completely different. K gamma dot power n with n less than 1, okay, less than 1. So potential. K is called consistency, it's related to how the fluid behaves, consistency, and n is called flow behavior index. These two parameters, K and N, are experimentally retrieved, okay? K and N are experimental, so we need to characterize them in that's what we talked about in the previous videos. You have to get them in the lab, okay? They're experimental. There's no experimental. It's not easy to, or maybe it's impossible, I don't know exactly the details, but you usually got experimentally. Okay. The third type, I have space if I keep, so you see both diagrams at the same time. The third type is called shear thickening. Remember, the shear thickening, viscosity increases with shear stress. This rheogram has this shape, this similar to the previous one, okay? Very similar, with the same names, but n now is higher than 1, okay? It's potential. Yeah. So the fourth type, the Bingham plastic, which was, remember, viscosity has like a step, and then, okay, is very similar to this Newtonian, but now this step, okay, the 4 is called yield stress. So yield stress means the force you need to release the fluid. So for the Bingham plastic, tau 0 is the yield stress, okay? It's a threshold, like in a door, you pass a threshold that you have to pass in order the fluid to move, okay? Yield stress. So the equation is very similar to this, but adding the yield stress. Tau 0 plus eta gamma dot, okay? And the final one, which is the non-Bingham plastic, yes, is the same behavior as the shear thinning, okay, but with yield stress. So like this, okay. Again, Tau 0 is the yield stress. It's initial stress you have to apply so it moves. Yeah, and then it behaves like a shear thinning. So the question is tau 0 plus k gamma n less than 1. Yeah, half a stand, have to go to it. Okay, yes. I gave you an example, remember in the previous class, about how this has to be done to characterize, because the equation describe the behavior, okay? The equations describe the how viscosity behaves, okay? Describe the behavior. The figures and the equations behavior can be used to predict heavy or. So I'll give you very quickly a couple of examples and then we are done. Okay? So the basic idea is that when you have a fluid, you have no idea how it works, what type of fluid it is. So you go to the lab, you put this spindle, it spins inside, that was called spindle, and then according to how the amortiguation, no, I didn't say amortiguation, I don't know, remember. So depending on how the fluid stops the spinning, you can obtain viscosity at different velocities. So you study these two rheograms, okay? So, and then why you do that? Because you have to fulfill some particular behavior when you design, for instance, medicines. For example, is eye drops. Eye drops are drugs that are administered through the eyes. Okay? Eye drops. So, some applications. Eye drops. Eye drops. Ophthalmic drops, also called eye drops. So the idea is that they are drops. Imagine that this is an eye, right? They come from a dropper and they come straight to the eye. Okay, this is the eye looking forward. Okay, yeah. Okay, I hope you imagine. So they have to have a certain pH. So pH, physiological, right? Physiological pH, same as the eye. You find around between 735 and 745. Physiological pH. Okay. And then the crucial part is that if they hurt, it will make us cry. The problem is not crying itself. There are some drugs or some treatments that are painful, and there's no problem if the benefit is good enough. But the problem in crying in the eye is that the crying, the tears drain the drug. Remember that brain dreams are drugs. By drugs, I'm talking about medicines. Drugs